Well, welcome everyone. I'm Bené Duncan with the Western Water Assessment at the University of Colorado Boulder. Thank you for making time in your schedules to join us for this webinar today, which is the second in a series exploring the recently released report, Colorado River Basin Climate and Hydrology, State of the Science. The first webinar was recorded and it's actually available if anybody's interested in watching it on the Western Water Assessment website. So for today, we will have a presentation of about 45 minutes, and then we'll use the remaining time for questions. This webinar will be recorded, and the video will be available on our website, and we will be sure to share that link with you after the webinar. Before we get started, I wanted to share a little bit about Western Water Assessment for those of you who haven't worked with us in the past. Western Water Assessment is an applied research program, and we address societal vulnerabilities to climate variability and climate change, particularly those related to water resources, as our name suggests. And while we're based in Boulder, Colorado and Salt Lake City, Utah, we work across the Intermountain West, and that includes Colorado, Utah, and Wyoming. Western Water Assessment is one of 11 teams in the NOAA Regional Integrated Sciences and Assessments, or RISA program. During today's presentation, you can ask questions with the Q&A chat window. And so if you look at your Zoom controls, you'll see a Q&A button, and click that and you can submit questions anytime during today's presentation. And we'll be saving those questions as they come in and be sure to answer as many of them as possible during the Q&A period at the end of today's webinar. And so now I'd like to introduce Liz Payton and Jeff Lukas, who were the co-lead authors and editors of the report, and Steph McAfee, the Nevada State climatologist at University of Nevada, Reno, who was the author of Chapter 4. So Liz is going to start us off, and then Steph and Jeff will join in.
Thanks, Bené. I'll provide just a bit of background on the report before we launch into the focused presentation. The past decade has seen a wave of new research relevant to the Colorado River Basin. The increasing complexity of data and models, combined with the uncertain hydroclimate and with upcoming negotiations in the basin, led a consortium of water providers to seek a synthesis report of the state of the science of the climate and hydrology in the basin. That consortium approached Western Water Assessment in the spring of 2018 to write that report. These are the entities who made up that consortium and sponsored the report: the Bureau of Reclamation, water resources agencies from the 7 basin states, plus some of the large water utilities in the basin, and the Colorado River District. We also received substantial technical assistance from NOAA's Colorado Basin River Forecast Center and the USGS. The organization of the report generally follows the flow of information that supports management and planning of water supply. That report has 11 chapters contained in 4 volumes. After the introductory material, each chapter has a particular focus and describes the data and methods currently used in basin planning and how they compare with other data and methods in that topic area. Each chapter ends with assessments of the challenges and opportunities for future progress in the particular topic. Observations of weather, climate, and hydrology covered in chapters 4 and 5 are the primary data in the complex chain of models and data. Ideally, the observations of all weather, climate, and hydrologic variables would have high spatial density to capture all the variation across the basin due to topography and other factors. And they would be 100% accurate, and they would have long periods of record with uniform measurement methods and reliability over time. In reality, of course, all observed records fall short of these ideal characteristics. It's important to understand the merits of any method or data set in the context of the intended application. Today, we will discuss the strengths and deficiencies of different observation networks and the methods for enhancing or supplementing those observations to alleviate the deficiencies. Here's the order in which we will talk about the weather, climate, and hydrologic variables. Starting with Steph's discussion of weather and climate observations. Then Jeff will talk about Snowpack observations. I'll discuss Streamflow, and Jeff will finish up with soil moisture and evapotranspiration and related observations. So I'll hand it off to Steph now.
Thanks, Liz. Now, of course, weather data are collected for a number of purposes, ranging from agriculture to transportation to water resources management. And while almost all weather stations collect temperature and precipitation data, they can differ substantially in terms of instrumentation and site location in order to best meet their design purpose or to accommodate practical concerns like getting to the station easily. And consequently, many do not follow the ideal station siting recommended by the World Meteorological Organization, which is shown here. And they suggest placing stations in large, flat, open areas far from trees, structures, and heat sources. So to go over some of these networks, the Co-op Observer or Cooperative Network is the largest and oldest in the US. It was designed to monitor weather and climate, and these stations collect temperature, precipitation, and sometimes snowfall. Many of these are run by volunteers, though a number are located at airports, national parks, weather service offices, and the like. And while these stations are widespread in the basin, they tend to be located in places with people. Because they are mostly manual stations, you often find them in places that do not meet ideal station siting guidelines put forth by the WMO. So here we see the Co-op station at Bryce Canyon National Park in Utah. It's a simple station with a rain gauge and temperature sensor. We see some tree cover near the site and also a parking lot, neither of which are ideal for long-term climate monitoring. The RAWS, or Remote Area Weather Station Network, was organized in the late 1970s and early 1980s. Its primary use is in monitoring fire weather. Consequently, they measure more variables than co-op stations, particularly wind and humidity. In addition, these stations, which are entirely automated, are typically deployed in remote areas, as their name suggests, but also in areas where wildland fire is a concern. So in the Colorado Basin, you can see that these tend to be located at some of the higher elevations. Now, another key network in the West is the SNOTEL network. These stations are designed primarily to measure snow for water resources management, but they do measure temperature and precipitation. Now, consequently, though, there are a number of things about SNOTEL stations that are particular to the network. First, they're in places where snow accumulates. And in the Colorado River Basin, that means many of them fringe the highest elevations at the edges of the basin. They have some additional instrumentation like a snow pillow, and the rain gauge is often particularly tall to avoid being buried in snow. Now, what I often see a lot of SNOTEL sites in relatively small forest gaps, and these locations may be more representative of snowpack, and as a practical consideration, trees may also protect these very expensive installations from avalanche damage. Now, like RAWS, the first stations in this network were deployed in the late 1970s. The last three networks shown here are all aimed primarily at understanding evapotranspiration in different environments, and they're largely in different locations than RAWS or SNOTEL sites. Now, but the end result is that the basin is monitored with a patchwork of different kinds of weather stations. And while they do all measure temperature and precipitation, they may not all measure humidity, wind, or snow. And in addition, different station networks may use distinct types of equipment and monitor specific areas. And as a result, some areas are more densely monitored than others. You can see from the map there are some substantial gaps in the northernmost part of the upper Colorado Basin and in parts of New Mexico. But the current station distribution is also not representative of past data availability. Of course, the number of stations in the basin was very low in the late 19th and early 20th centuries and has been growing since. Now, this, of course, leaves us with the question of how we can use weather station data that have gaps in both space and time to create the temporally and spatially complete data that models usually need. So we often turn to gridded products. These are data produced on a regular grid where each cell has a value for each time step. They can be produced using statistical interpolation or physically based models. Higher resolution products where the grid cells are less than about 10 kilometers by 10 kilometers are more commonly developed with statistical methods and often provide monthly or daily data. So this figure here shows the NRCS map of weather stations that provide precipitation data around Crested Butte, Colorado. There are 3 SNOTEL stations indicated, as well as one marked ACES. And ACES is a database that serves data from co-op and other networks. Now, assuming an approximately 4 kilometer by 4 kilometer grid on par with many high-resolution gridded products, there is station coverage in roughly 4 of the 35 grid cells that cover the area. This is actually pretty good station coverage, and many areas will not have this much station data to work with. But even in areas like this with generous station coverage, there are still many choices to be made about how to develop a value for every grid cell. And like station observations, gridded products are often developed for a specific purpose, and purpose tends to guide those choices. The first choice is which stations to use. There's a limited pool of stations available to choose from, and while dataset developers may identify different sets of stations to use, there's likely to be a fair amount of overlap in the input. This means that gridded data products aren't fully independent. Some of them, like GridMet, which you can see on this figure, even rely directly on other gridded products. Now, one of the next major choices is about whether or not to correct for inhomogeneities. Now, an inhomogeneity is any reflection of non-climatic influence in the data. These are commonly associated with things like changes in the station location or the type of equipment used, but they can also develop with a change in the surroundings. And while combining data from multiple stations can limit how strongly these inhomogeneities show up in the data, they can creep into the final gridded product. So data sets that are developed for trend analysis, like topo weather in the yellow, tend to correct for inhomogeneities, although that can mask some fine-scale climate features. Products like Prism in the sort of turquoisey blue that are focused on spatial representation don't correct for inhomogeneities, so aren't as good for trend analysis. Now, dataset developers may also need to make choices about how to account for lapse rate, the change in temperature with elevation, and whether or not to include information about cold air pooling, aspect, or anything else that can influence temperature. Consequently, we see some real similarities in temperature plots for the upper Colorado Basin. The same years are very warm or very cold in all data sets, and all data sets display similar warming trends in recent decades. The largest differences, mostly in mean temperature, are early in the data set when station availability is lowest. And in the minimum temperature series, it actually becomes very clear that using a fixed lapse rate, as some products do, leads to an underestimate of the minimum temperatures and much cooler conditions in the basin. Precipitation also varies across the landscape, but often not in as straightforward a manner as temperature. And as a result, many data products use the Prism climatology developed by Chris Daly to impose spatial differences in precipitation. And this is perhaps one reason why precipitation data displays such consistency across the basin in terms of mean precipitation as well as extremes. Although the development of gridded climate data has allowed for significant developments in our understanding of hydrology, there are still caveats to these data as well as opportunities for improvement. And it's important to remember that climate data are produced for specific reasons, and if you're using them off-label, it's worth being careful. So thinking about some of the challenges and opportunities, we know that these data are imperfect, particularly in their ability to represent very fine-scale climate patterns. And there are open questions about the consequences of using imperfect data. But there are opportunities as well. New, smaller, and cheaper monitoring equipment is providing the opportunity to investigate finer scale variability in climate. High-resolution modeling can create physically realistic data without dense observations, as well as identifying areas where more intense on-the-ground monitoring will give us the most bang for our buck. Finally, recognizing that there isn't a single best climate product for every need frees researchers and managers from trying to find one, and instead lets them focus more on pertinent questions such as evaluating different product strengths and weaknesses for given applications. So now I will turn it over to Jeff to talk about Snowpack observations and monitoring.
Thanks, Steph. We begin our discussion of hydrology observations with Snowpack because most of the annual water supply in the basin likewise begins as Snowpack. The Snowpack is really the interface between meteorological processes and hydrological processes. Weather and climate really drives the Snowpack. The accumulation of snow during individual storm events, its redistribution by the near constant winter winds, losses of snow to sublimation, and of course snowmelt, which is driven by the sun and warm temperatures. The interactions of all of these processes with the complex terrain and with forest canopies results in snowpack that is very dynamic and variable over both space and in time. That said, many aspects of the spatial pattern and seasonal trajectory of the basin's snowpack are fairly consistent from year to year. But the evolution of the snowpack in any given year can diverge from the general patterns, influencing the magnitude and the timing of snowmelt runoff. When our snowpack monitoring is unable to capture these anomalies, it leads to larger errors in the seasonal runoff forecasts. The most important metric, of course, for snowpack monitoring and forecasting of water supply is snow water equivalent, or SWE. SWE is measured directly through in situ observations, such as shown here, modeled from meteorological observations like those Steph described, or derived from measurements of snow depth and estimates of snow density. For over 80 years, snowpack monitoring and water supply forecasting in the Colorado River Basin and throughout the Western US has relied on a network of in situ ground-based observation sites managed and maintained by the NRCS, along with many state and local cooperators. Over the last few decades, the manually measured snow courses, as shown at left, have been supplemented or replaced by automated SNOTEL sites, shown at right. Currently, there are about 250 SNOTEL sites and still about 130 snow courses across the Colorado Basin, most of them in the upper basin. The observations from this SNOTEL and snow course network in most years and in most locations provide reliable indications of snowpack conditions in their respective catchments. However, there are several general limitations in the network coverage. SNOTEL sites are not located above tree line or on steeper slopes and southerly aspects, or at lower elevations where snowpack is generally low or intermittent. Thus, in those years with unusual spatial patterns or temporal patterns of snow accumulation, the SNOTELs and snow courses will not capture the actual SWE conditions across watersheds and basin, as well as in a more typical year. So then, spatially explicit depictions of the snowpack are designed to compensate for the limitations of the SNOTEL network. They also provide insights into processes and patterns that are difficult to glean from the in situ point observations alone. It's important to note, though, that spatial products, like the one on the right, are not independent of the underlying SNOTEL observations on the left. All of the products calibrate and validate their models on SNOTEL data or directly assimilate SNOTEL data, or both, to inform the spatial estimates of SWE. The several spatial snow products that are currently available are constructed in different ways. Most merge SNOTEL observations, gridded weather data as described by Steph earlier, and sometimes satellite data of snow cover within a statistical or physics-based snow model. This produces estimates of SWE and other variables for each grid cell, just like the gridded weather and climate products. The Airborne Snow Observatory, or ASO, shown at far right, starts with a grid of airborne LiDAR measurements of snow depth and then integrates modeled snow density. For operational stream forecasting at the Colorado Basin River Forecast Center, CBRFC, they used the Snow 17 snow model and SNOTEL and co-op precipitation observations to estimate a snow water volume for each modeling unit, which is then translated into a spring-summer streamflow volume. The snow model, like all of the spatial products, allows the modeled snow to persist at the highest elevations in late spring, even after the SNOTEL sites have melted out, consistent with the real-world behavior of the snowpack. Another gridded or spatial product is the Snow Data Assimilation System, SNODAS, that was developed by NOAA's National Operational Hydrologic Remote Sensing Center, or NORISC. This center has actually produced daily operational SNODAS products since 2004. SNODAS estimates multiple snow characteristics on a daily basis by merging satellite, airborne, and in situ snow data from SNOTEL and other networks, including co-op and COCORAS, in a physically based energy and mass balance snow model driven by meteorological data. The variables modeled include SWE, snow depth, snowmelt, sublimation, and snowpack temperature. In its early years, SNODAS was not very well tuned to our mountain snowpacks and was less reliable, but many improvements have been made to its inputs and model scheme. Studies that have compared SNODAS with high-density field sampling indicate that the SNODAS snowpack estimates are reasonably accurate and useful at watershed scales, though less so at the single pixel, that is 1 kilometer, to 10 kilometer scale. This is likely true of all spatial products except ASO. The SWANN modeling system is a research product developed at the University of Arizona by Patrick Broxton and others. It uses snow models, SNOTEL SWE data, and artificial neural networks, which is a type of machine learning algorithm, to generate gridded estimates of SWE and snow cover. The SWANN daily SWE estimates are available back to the early 1980s. The developers of SWANN have also created the map-based web tool shown here called SnowView to visualize and access SWANN SWE estimates for basins across the US. And finally, the Airborne Snow Observatory, ASO, is an aircraft-based platform developed by NASA JPL in 2013 and now operated by a private company led by former NASA researchers. It carries a scanning LiDAR sensor that can measure snow depth very accurately and precisely to the nearest 10 centimeters, 4 inches. Observed or modeled snow density is then used to translate the snow depth data into SWE, resulting in a very detailed spatial SWE product at a 50-meter horizontal resolution, as shown here for the area around Crested Butte. ASO data are the closest thing that we have to truth for spatial variability in SWE across large areas. But as they say, no plane, no gain. ASO has primarily been deployed in the Sierra Nevada. In our region, ASO has been flown as part of pilot projects in the Uncompahgre Basin, the Gunnison, and in the Blue River. Typically 1 to 6 flights are carried out per basin per season. The CBRFC and researchers with ASO are currently working to evaluate the ability to incorporate ASO data into the CBRFC forecast models to improve streamflow forecasts. Looking into the future, we have to keep in mind that the current snow monitoring and streamflow forecasting systems have been largely built on the assumption of stationarity, that climate and SWE conditions at SNOTEL sites will maintain their statistical and model calibrated relationships with seasonal streamflow. This assumption is increasingly complicated by warming temperatures and changing patterns of the snowpack. The usefulness of our in situ measurements of snow alone as predictors of runoff volumes is at risk of being degraded in the future. But we can also see indications that snowpack monitoring is evolving in the basin and across the West to become more robust in the face of both year-to-year variability and long-term climate change. SNOTEL observations are being increasingly augmented by the Spatial snowpack products. Those products are feeding into Streamflow forecast systems that are themselves evolving to better handle spatial information and accommodate changes in key physical processes. The CBRFC, as well as NRCS, are continuing to act as test beds and integrators of these new snow data and methods in partnership with university, agency, and private sector researchers. So to summarize the challenges and opportunities in snowpack observing, first, our inadequate quantification of the snowpack, particularly in certain years, is still a major source of error in Streamflow forecasts. And these anomalous patterns appear to be occurring more often in a changing climate. And then while we have these new spatial SWE data sets, there have been few rigorous evaluations of them, in part because it is difficult to validate spatial products. And then despite the essential nature of the SNOTEL network, it has been inadequately funded in recent years, really over a decade. So the opportunities are first to build on recent pilot efforts to conduct larger scale systematic intercomparisons of SWE data sets and products for the basin, including SNOTEL, ASO, SNODAS, and other spatial products. And then based on the results of those intercomparisons, pursue hybrid approaches where multiple methods and data sets are combined in a way to best exploit the relative advantages. And then step up the currently slow expansion of the SNOTEL network, which would necessitate more resources for NRCS. Now I'll hand it back to Liz to talk about Streamflow observations.
Thanks, Jeff. Streamflow observations in the Colorado River Basin have formed the basis for the agreements, decrees, treaties, and compacts that comprise the law of the river. They are critical to ongoing management and operations of all aspects of Colorado River Basin water supply today. The USGS is the primary entity that operates and maintains stream gauges. Within the Colorado River Basin, Reclamation, the basin states, and dozens of other entities also maintain, operate, and fund stream gauges through their participation in the Cooperative Water Program. USGS performs quality control and is the central clearinghouse for data collected through this program. Near real-time Streamflow data, as well as historical Streamflow data, are available for these stations through the National Water Information System, shown here. The USGS provides assessments of the gauge quality of each Streamflow gauge. These assessments depend on the stability of the stage discharge relationship or rating curve, which is used to convert the observed water elevation to Streamflow. Uncertainties in Streamflow data arise from errors in the rating curve, changes in the stream channel or vegetation, too few opportunities to capture and represent extreme high or low flows, and instrumentation errors. McMillan et al. Estimated the combined uncertainties found in Streamflow observations. They found about 50 to 100% uncertainty for low flows, 10 to 20% for medium or high in-bank flows, and 40% for out-of-bank flows. A subset of USGS gauges are part of the Federal Priority Stream Gauge Network, a group of gauges that are considered critical for federal support of forecasting, compact and border agreements, analysis of long-term trends, and other purposes. The FPS gauges are supported through a combination of federal and partner funding. Less than 1/4 are fully funded by the GS. The agency uses the FPS designation to indicate those gauges that the USGS classifies as critical and thus eligible for FPS funding as available from federal appropriations. The green dots on the map are active FPS gauges, and the white dots are proposed gauges. The primary stream gauging locations used for reclamation's planning and operations models in the Colorado River Basin generally line up with the inflow locations shown on these maps. On the left are the inflow locations for the 24-month study and the midterm probability and operations models. The inflow numbers on the map on the right, the CRSS map, are keyed to the USGS station names in the next slide. This slide shows the record lengths for each of the gauge locations corresponding to the 29 inflow points in CRSS. The stations have varying record lengths and therefore have varying levels of overlap with each other. In 1983, Reclamation extended the naturalized streamflow records back to 1906 for all the gauges that started after 1906, and that process was then repeated with a more sophisticated statistical approach in 2006 by Lee and South. Streamflow data obtained directly from gauges reflects upstream natural processes and human activities such as diversions, agricultural return flows, and reservoir operations. The time series reflects changes in those natural processes and human activities over time as climate, vegetation, and land use in the basin change. The process of adjusting gauge observations to calculate stream flows that are restored to natural, unimpaired levels is called naturalization. The level of adjustment depends on the application and availability of data quantifying upstream activities. This table shows the naturalized streamflow data that have been created for the Colorado River Basin by various entities for differing purposes. The report describes each of these products in some detail. Today, I'll just go into the methods used by Reclamation and the CBRFC. To develop the monthly natural flows that are input to CRSS, the Colorado River Simulation System model, Reclamation adjusts gauge streamflow data for reservoir operations and consumptive use. The specific adjustments made to calculate the natural flow for upper basin locations differ from those of the lower basin. It uses records and estimates of consumptive uses and losses, combined with changes in reservoir storage and losses due to reservoir evaporation, to adjust historical gauge flows in the Riverware modeling system. This figure shows the resulting Colorado River at Lee's Ferry natural flows compared with the original measured gauge flow. The gray line is the net adjustment made to the gauge to arrive at unimpaired natural flows. You can see how, after Lake Powell was completed in 1963, the adjustment to the gauge is occasionally negative, reflecting that the releases from Lake Powell occasionally exceed the entire natural flow of the river there. The natural flow data set available on the Reclamation website is actively maintained and updated with recent natural flow values. Annual updates are posted once all of the components have been compiled and adjustments made, about 12 months after the end of the year. In addition to adding to the natural flow record as each year's data becomes available, Reclamation also frequently refines its natural flow calculations using new information and methods. These refinements affect previous year's natural flow values. Reclamation documented these refinements and made them available to us in a spreadsheet. An example from the 2013 set of refinements is shown in this slide. The bullets describe the adjustments made, and the graph shows the magnitude of the adjustment. The big adjustment made that year was to the way bank storage in Lake Powell is calculated. Reclamation's natural flows are retrospective estimates. The CBRFC forecasts monthly unregulated flows for basin locations corresponding to upper basin inflow points in Reclamation's 24-month study and MTOM models. For those applications, the CBRFC's unregulated flows are gauge flows that have been adjusted for some, but not all, upstream activities, and thus are not as fully naturalized as natural flows. The CBRFC takes observed flows and removes the effects of measured upstream diversions, exports, imports, and reservoir regulation. The formula for CBRFC's unregulated flow calculation, in which all of the terms are taken from observations, is shown on the slide and illustrated in the process diagram. For other applications, the CBRFC does estimate unmeasured depletions. Besides having very different applications, the primary difference between CBRFC's unregulated flows and Reclamation's natural flows is the treatment of upstream diversions and return flows. Upstream activities that are either not measured or for which data is unavailable in a routine and timely manner are not backed out of the observed gauge flow in the CBRFC version. Through our synthesis work on streamflow observations in the basin, we identified these challenges. Streamflow observations that could contribute to more accurate representation of the basin hydrology are not available at many key sites, especially at diversion and return flow locations. The natural flow record, because it is regularly being refined and improved, is something of a moving target. This has implications for a number of research activities that use Reclamation's natural flow record for baseline or reference purposes. And lastly, fully characterizing the natural hydrology of the basin is problematic with the exclusion of the Gila River from consideration. And we identified these opportunities. Expanding the streamflow monitoring network to fill gaps in coverage is key. This includes gages at diversion sites and in locations to measure return flows or verify return flow and gain loss calculations. Increasing the spatial resolution of Reclamation's models and therefore representing more streamflow locations might be a useful avenue to pursue in order to simulate and analyze impacts from climate change on sub-basin hydrology. And finally, major modifications to the natural flow record to improve consumptive use estimates, for example, have implications for both the research activities that use Reclamation's natural flow record and for the record extension back to 1906. As more data becomes available, there is an opportunity to revisit the characterizations, calibrations, bias corrections, and record extensions that were based on earlier versions of the natural flow record. With that, I'll hand it back to Jeff.
Okay. So soil moisture, like snowpack, is an interface between atmospheric and hydrologic processes. We often think of soil moisture in the context of crops, but on a basin scale, it is also a huge bucket temporarily storing millions of acre-feet of water that may or may not become runoff. Like snowpack, soil moisture integrates precipitation and evapotranspiration over long time periods, imparting memory to the hydrologic system. In particular, the soil moisture in the fall going into the snow season is a major influence on runoff efficiency for the following spring. Thus, soil moisture is a key component of the CBRFC streamflow forecast model. Until 20 years ago, in situ observations of soil moisture in the Colorado Basin were extremely sparse. But about 100 soil moisture observing sites have been established in recent years, with most of them located in the upper basin. By far, the greatest number of these are at SNOTEL sites, shown in light blue on the map. Outside of the SNOTEL network, at lower elevations, the in situ monitoring is still very thin. Even in the better monitored high elevations, soil moisture is so spatially variable that it is difficult to construct a coherent picture from in situ observations alone. Accordingly, CBRFC uses modeled soil moisture that is simulated from gridded climate data in their streamflow forecast model. Here we see from last fall that low soil moisture in much of the upper basin that ultimately pushed down the spring runoff volumes in 2020. New remotely sensed data on soil moisture from satellites have the potential to augment and better tie together in situ and modeled soil moisture data, though most remotely sensed data only extend through the top 10 centimeters of soil, whereas it is a deeper soil moisture profile down to a meter or more that influences runoff. Several other spatial soil moisture products are available for the basin. Most use observed meteorological inputs, like in the CBRFC model. Other products are based on remotely sensed data. There are ongoing efforts to integrate in situ, modeled, and remotely sensed soil moisture into blended products through the National Soil Moisture Network, as shown in this product here. So the challenges and opportunities for soil moisture observations. First, soil moisture is incredibly spatially variable and inadequately monitored, and has large discrepancies between the in situ observations that are made and gridded modeled estimates. And then the real-time soil moisture data that is collected comes from at least 6 different in situ networks that have different observing protocols. The opportunities are, first, to support and expand ongoing efforts to comprehensively collate in situ soil moisture measurements and merge these observations with spatially distributed modeled estimates. Second, there are new satellite sensors and products that can provide spatially comprehensive and consistent soil moisture estimates to be compared and blended with other types of data. And then, when applicable, conduct testing of the new soil moisture products to determine if they add value to the CBRFC and NRCS Streamflow forecast process. So we're going to end our tour of hydrology observations with what is actually the largest term in the basin's overall water budget, evapotranspiration, the combination of evaporation and transpiration from plants, by which about 90% of the precipitation falling all across the Colorado River Basin returns to the atmosphere. Related metrics include open water evaporation and evaporative demand. Estimates of one or more of these variables play key roles in management activities like reservoir operations, irrigation scheduling, and consumptive use monitoring, and also in constraining the water budget as simulated by different types of system and forecast models. Generally, evaporation-related variables are estimated using a model driven by meteorological observations, or they're derived from remote sensing data. Direct in situ measurements of these evaporation-related variables are very sparse. Open water evaporation in large reservoir settings is notoriously difficult to quantify, and many different methods have been used in the past in the Colorado River Basin and elsewhere. Since 2010, USGS and Reclamation have partnered to produce real-time evaporation estimates for Lake Mead and Lake Mojave using the more physics-based eddy covariance and Bowen ratio energy balance methods. The results will be used to revise projections of future evaporation for use in system models like CRSS and MTOM. Currently, Reclamation is partnering with the Desert Research Institute to compare evaporation estimates for Lake Powell using multiple methods on one observation platform as shown in the photo. This effort will try to establish which of several methods have the highest potential for long-term operational monitoring given accuracy, cost, and other considerations. Actual ET, which is shorthanded as AET or ETA, is equally difficult to quantify over large areas. Direct measurements, as shown at left from an eddy covariance flux tower, is done at a relatively small number of existing sites and can't be readily scaled up to basins. But these in situ measurements are still critical for validating estimates from other methods. More frequently, actual ET is estimated using one of several indirect methods involving meteorological inputs and crop coefficients, or using a land surface model, and or using satellite observations of land surface temperature in an energy balance model, as is shown in the USGS product at right. The Upper Colorado River Commission, with the 4 upper division states and Reclamation, have partnered on a multi-year study, now in its 3rd phase, to assess and improve estimates of consumptive use from agriculture. This study is reviewing the different methods currently used to estimate AET, including newer remote sensing-based methods. Finally, evaporative demand, shorthanded as ET0 or ET0, is a measure of the thirst of the atmosphere. It is the maximum rate of evapotranspiration under given atmospheric conditions and an unlimited supply of water. Thus, it is effectively the same as reference ET or potential ET, which is shorthanded as PET or ETP. Evaporative demand is usually computed using one of several formulations that require meteorological inputs. The preferred one is Penman-Monteith, incorporating 4 key variables: temperature, humidity, wind speed, and solar radiation. Shown here is the Evaporative Demand Drought Index, or EDI, which uses this formulation along with gridded meteorological data to quantify the relative evaporative demand over multiple timescales and is increasingly used in monitoring for multiple purposes in resource management. So the challenges for evaporation and ET observations: first, with reservoir evaporation, the estimates as currently used in basin system modeling have been based on decades-old data that does not reflect current climate conditions. Then for actual evaporation or actual evapotranspiration and crop water use, currently used estimates have been constrained by physically incomplete methods in many cases and input data that are not spatially representative. So the opportunities include ongoing efforts to provide updated reservoir evaporation estimates for Meade and Powell. And then these efforts could be expanded to other large reservoirs in the basin. Second, for AET, more in situ monitoring with enhanced weather stations that capture all 4 variables needed for fully physical estimates and new flux towers needed for the eddy covariance method would really help give us a fuller picture of evaporation and evapotranspiration over the basin. And then better in situ data will also help in calibrating and validating remote sensing-based spatial estimates of AET and crop water use. The use of these spatial estimates in the basin has been increasing, though it has been limited so far by user confidence in the data. So to summarize, across the different types of weather, climate, hydrology observations discussed today, the in situ observation networks like NOAA's COOP, NRCS SNOTEL, USGS, and partner stream gauges are all still absolutely essential for our retrospective understanding, our real-time monitoring, and baselines for future planning. The rapidly emerging spatial perspectives and products leverage and extend the reach of the in situ networks, providing enhanced monitoring capacity. But these new techniques and products in no way replace the foundational observation networks. And in all cases, in order for scientific and technical advances in observations to be incorporated in that chain of models that informs water planning and management in the basin, the operational agencies and personnel, streamflow forecasters, water planners, water engineers, need to be meaningfully involved in the research, even before any pilot applications. The report does document many past and ongoing research to operations efforts that have done this, and we expect to see that continue into the future. Along these lines, last fall, USGS announced that its second Next Generation Water Observing System, or NGWAS, would be located in the Colorado headwaters above Cisco, Utah, plus the Gunnison Basin. This advanced observing system will build on existing networks to provide data on streamflow, ET, snowpack, soil moisture, water quality, groundwater, surface water connections, and water use. This year, USGS is doing planning and stakeholder engagement to shape this effort to most effectively enhance the observing capacity in these key watersheds for the upper basin. We'll put the URL for the project homepage, which has contact info, in the chat window. So that completes our main presentation. Liz has a few words about a call for papers, and then Benet will moderate the Q&A.
Thanks, Jeff. I'd like to take a half a minute to let people know about a special issue of the Journal of the American Water Resources Association commemorating the 25th anniversary of severe sustained drought Managing the Colorado River System in Times of Water Shortage. The anniversary issue will be edited by George Frisbold with co-editor help from me, Steph, Connie Woodhouse, Jack Schmidt, and others. We are encouraging submissions that reflect on the original studies and provide new insights on implications of multi-decadal drought in the Colorado River Basin. Submissions considering the effects on water quality, public health, and vulnerable border and tribal communities are also welcome. We are requesting abstracts and expressions of interest by the end of this month, August 31st. Please consider contributing to this landmark issue by providing your 21st century view of the river. Thank you.
Thanks so much to Liz, Steph, and Jeff for the great presentation. I learned a lot just listening to everybody go through their slides today. And thanks so much to those of you who have already submitted questions in the Q&A box. Please feel free to keep them coming. Just look for the Q&A button in your Zoom control panel, and it'll let you submit questions that way. And so with that, let's start to answer your question or your questions until noon. And I'm going to start with a really easy question, and that was, Liz, we have a question. Just could you remind us what journal the special issue is in?
Yeah, it's the Journal of the American Water Resources Association, and there's a link in the chat to that call for papers. It's the one just above the one Jeff just posted. So. Great,
thank you.
Mm-hmm.
Awesome. Let's see. And then the first question I will pose to you all, it kind of integrates across some of the things we've talked about today and is a very timely question. And that is, can you draw any conclusions between stream flow and wildfire on the west slope? Do you have any suggestions or ideas or recommendations as to how or if we can make watershed level conclusions?
Let me, I'll try to take a crack at that. I mean, in general, a large wildfire will have, potential consequences for both water quality and potentially water quantity as well, depending on the forest type or vegetation type that it's in, and the geology, the soils, the elevation. So it's hard to generalize. I mean, clearly, the water quality, impacts or potential impacts are maybe the most obvious. We've had many examples of that after fires, large fires in Colorado over the last few decades. For water quantity, if you burn off a lot of forest cover and vegetation over a large area, you would expect not only degraded quality of runoff, but potentially higher runoff from individual events. It's not clear how it would work out seasonally in our snowmelt dominated higher elevation watersheds. So I think, I imagine this question is in reference to the very large wildfires that we have on the west slope, including one that's right along the banks of the Colorado River in Glenwood Canyon. I think we'll just have to kind of keep an eye on these, see how the burned area looks, and try to, make some, guesses as to, what the implications might be for that particular burn area and watershed, after, assessing the particulars of that case.
Great, thanks, Jeff. Let's see, and I've got a question that I think I might direct towards Liz, but feel free to redirect if needed, Liz. And that is, are natural flow estimates used to inform any operations or compact compliance? Or are they more used for benchmarking and referencing? Could you just kind of share an example of how natural flow estimates are useful?
Well, the Reclamation's monthly natural flow sort of retrospective values are used in a lot of the long-term planning studies that Reclamation and others use. or do. They were used in just the 10 tribes partnership study recently. They were used in the drought contingency planning efforts throughout the basin. They've been used in the 2012 basin study. So they're used quite a bit in long-term planning. For the they're not so much used in operations, and there are probably reclamation people listening, and hopefully they will speak up or wave or something if I've got this wrong. But in general, for the operations kind of work, they use the CBRFC's unregulated flows and a slightly modified version of that Reclamation uses. So I hope that helps answer the question. But if you look at our report, you'll see a table of all the places where natural flows have been used.
Awesome, thank you.
Mm-hmm.
Let's see, and we've got 3 minutes left, and I've got a number of questions, so maybe we can kind of lightning round it a little bit and see how many we get through. And whatever we don't get through today, just know that we will keep a record of these questions and try to take a look at them, or you can feel free, of course, to reach out directly. And so one question that's come in is, what new satellite data is coming online that may help with any of the climate data discussed today?
I can take a very quick crack at this one. It's not my expertise. There are probably people attending who know better than I do. But of course, the recent couple years ago launch of GOES 17 was really helpful, is pulling in some more weather data in the western areas. But one place where we're also seeing big expansion is in some of those lower platform based things. So aircraft based products like ASO, now even some drone based monitoring that can really help getting into areas where we don't have in situ or on the ground monitoring. And that is happening sort of on a number of fronts in different places as people are testing out new platforms and new methods.
Great, thank you, Steph. Let's see, and I'm going to ask one last question today, and that is, in regards to global warming and long-term impacts, are we expecting to experience a highly variable impact on future water resources? So like, would we expect many catastrophic flood years followed by many drought years, or are we expecting consistently dry conditions? Can any of you speak to that?
Yeah, so I think the answer based on projections of hydrology informed by climate models, showing future temperature and precipitation scenarios for the basin, suggests that it's a little bit of both, that we're expecting conditions to become overall drier, but not consistently dry every year. There's definitely rising temperatures alone create a strong push of the water cycle towards more arid conditions because of rising evapotranspiration. And we're also seeing in the climate model output a tendency of increased variability from year to year and maybe season to season that is going to be enhanced by feedbacks from the land surface. So I think, yes, our flood years or our wet years could become a little wetter. The dry years definitely, drier. So we'll have this greater variability between extremes. So maybe not a whole lot more than we already experienced, but superimposed on a declining baseline towards a drier hydrology.
Great, thank you, Jeff. And so we're out of time today. And I want to be respectful of everybody's schedules and let you all head out. So thanks so much to everybody for joining today's webinar, and to Liz, Jeff, and Steph for their great presentation and for answering our questions. And remember, you can download the full report report and view other resources on Western Water Assessment's website. And we'll also be posting a recording of this webinar there. So we'll be sure to share the link with all of you when it's posted. In the meantime, please feel free to reach out to us if you want to keep the conversation going. Email addresses are on the slide that we're sharing now. Thanks so much. Have a great day.